Hello, welcome to Astronautics for Exploit. I am Dr. Ayenshola Ogundele, and I will be presenting Orbital Spaceflight. The overview of my presentation is as follows. Orbital flight versus suborbital flight, orbital launch, orbital space station, free fall versus weightlessness in orbit, and orbital decay. Human being, in its curious nature, and guess for knowledge advancement, progress, and betterment of humanity, always seek for new innovative ways of exploring space, visit the cosmos, and go for vacation in space via space tourism. Continuous improvement and development of launch vehicles technologies, iteratively and incrementally, through agile methodology, which value individuals and interactions, offer processes and tools, working software over comprehensive documentation, customer collaboration, over contract negotiation, and responding to change over following a plan is helping in achieving reusable rockets, which is needed for uninterrupted space exploration and orbital spaceflight activities. Orbital spaceflight, a spaceflight in which a spacecraft is placed on a trajectory where it could remain in space for at least one full orbit, is gaining increased attention due to government, space agencies, and private space companies' high interest in space economy, which is made possible through orbital and suborbital space tourism, production, trade, commerce for goods and services produced through the space spinoff. All these activities are creating new world of possibilities for humanity. Orbital spaceflight from Earth has only been achieved by launch vehicles that use rocket engines for propulsion. In order to reach orbit, rocket must impart to the payload a delta V of about 9.3 to 10 kilometers per second. The main technology involves launching nearly vertically for a few kilometers while performing a gravity turn. There have been many proposed methods for achieving orbital spaceflight that have the potential of being much more affordable and reusable than rockets. Some of these ideas are space elevator, rotorcraft, grand accelerators such as launch loops, rocket-assisted aircraft, and space planes. Over the years, SpaceX has demonstrated and is still demonstrating significant progress in their incremental approach to reducing the cost of orbital spaceflight and making the rockets reusable. Orbital spaceflight. An orbital spaceflight, a spaceflight that achieved orbital velocity and also known as orbital flight, is a spaceflight in which a spacecraft is placed on a trajectory where it could remain in space or Earth's orbit for at least one full orbit. An example of orbital spaceflight is found in to and fro traveling to the International Space Station. The picture here shows International Space Station. Altitude at closest approach. To achieve an orbital spaceflight around the Earth, a spacecraft must be on a free trajectory and have an altitude at perigee. Altitude at closest approach around 80 kilometers, that is 50 miles. This is the boundary of space as defined by NASA, the US Air Force, and the FAA. In order to remain in orbit at this altitude requires an orbital speed of approximately 7.8 kilometers per second. The picture here shows SpaceX Crew Dragon for orbital spaceflight. Federation Aeronautique Internationale FAI established the command line at an altitude of 100 kilometers as a working definition for the boundary between aeronautics and astronautics. At command line, as calculated by the Theodor von Kármán, a vehicle will have to travel faster than orbital velocity to derive sufficient aerodynamic lift from the atmosphere to support itself. The picture here shows Theodor von Kármán. At higher orbits, orbital speed is slower, but to attain the speed requires higher delta V. Delta V is a concept used in spacecraft flight dynamics. It is a measure of the impulse per unit of spacecraft mass that is needed in order to perform a maneuver, such as launching from or landing on a planet or moon, or an in-space orbital maneuver. This picture shows SpaceX Crew Dragon. Orbital flight versus suborbital flight. Suborbital space flights are flights where the apogee of a spacecraft reaches space, but the perigee is too low. Unlike suborbital, which reaches an altitude of about 100 kilometers and gives passengers a few minutes in space, orbital missions reach an altitude of over 400 kilometers and spend days or even more than a week in space. Astronauts can also spend months and years in space. This picture shows Blue Origin suborbital flight of July 20, 2021 with founder Jeff Bezos on board. The second picture shows Virgin Galactic's suborbital flight of July 11, 2021 with founder Richard Branson on board. Difference between orbital and suborbital spaceflight. The main difference between orbital and suborbital flight is that an orbital spacecraft must achieve orbital velocity, whereas a suborbital rocket flies at a speed below orbital velocity. Up to date, orbital space tourism has been limited to few flights to the International Space Station and SpaceX inspiration for orbital flight. This picture shows SpaceX's first all-civilian orbital spaceflight, which took place on September 15, 2021. Orbital launch. Orbital spacecraft from Earth has only been achieved by launch vehicles, which make use of rocket engines for propulsion. Requirements to reach orbit. In order to reach orbit, rocket must impart to the payload a delta V of about 9.3 to 10 kilometers per second, which are approximately 7.8 kilometers per second for horizontal acceleration, which is needed in order to reach orbital speed, but allows for atmospheric drag, approximately 300 meters per second, with a ballistic coefficient of a 20 meters long dense fuel vehicle. Gravity losses, depending on burn time and details of the trajectory and launch vehicle, and gaining altitude. This picture shows SpaceX Falcon 9 launch vehicle. Main launch vehicle technique. The main proven technique involves launching nearly vertically for a few kilometers while performing a gravity turn and then progressively flattening the trajectory out at an altitude of more than 170 kilometers and accelerating on a horizontal trajectory with the rocket angled upwards in order to fight gravity and maintain altitude for about 5 to 8 minutes burn until orbital velocity is actually achieved. Requirements to reach orbit. Currently, about 2 to 4 stages are needed to achieve the required delta V. Most launches are by expendable launch systems. This picture shows Blue Origin New Glenn launch vehicle. Launching proposed methods. There have been many proposed methods for achieving orbital spaceflight that have the potential of being more affordable and reusable than rockets. The proposed new ideas are space elevator, rotovator, ground accelerators such as launch loops, rocket-assisted aircraft or spaceplanes such as reaction engine Skylon, scramjet-powered spaceplanes, and RBCC-powered spaceplanes. Another proposed idea is gun launch, which has been proposed for cargo. This picture shows space elevator. Orbital space station. A space station, which is also known as an orbital space station, is a spacecraft which is capable of supporting a human crew in orbit for an extended period of time. Space station, a type of space habitat, lacks major propulsion or landing systems. Stations must have docking ports so as to enable spacecraft to dock and transfer crews and supplies. Space stations are mostly launched for scientific purposes. This picture shows astronauts, human crew, on board the International Space Station orbiting the Earth. Current orbital space station. We have International Space Station from 1998 up to present. ISS is a modular space station, an habitable artificial satellite in low Earth orbit. It is a multinational collaborative project which involves 5 participating space agencies: NASA, Roscosmos, JAXA, ESA, and CSA. The station serves as a microgravity and space environment research laboratory in which scientific research is conducted in astrobiology, astronomy, meteorology, physics, and other fields. This picture shows International Space Station. Another current orbital space station is Tiangong Space Station between 2021 up to present. It is owned by China, and the first module of the space station was launched on 29 April 2021 into a low Earth orbit, 340 to 450 kilometers above the Earth at an orbital inclination of 42 degrees to 43 degrees. It's planned to be constructed through 11 launches across 2021 and 2022. The core module will be extended with 2 laboratory modules, which is capable of hosting up to 6 crew. The purpose of the space station is for the development of spacecraft and transport technology, breakthrough in key technologies, for example, permanent human operations in orbit. This picture shows Tiangong Space Station. Free fall versus weightlessness in orbit. Free fall is the motion of a body where gravity is the only force acting upon it. In the context of general relativity, where gravitation is reduced to a space-time curvature, a body in free fall has no force acting on it. The Moon is thus in free fall around the Earth, though its orbital speed keeps it in very far orbit from the Earth's surface. Space is nearly a perfect vacuum. Beyond Earth's atmosphere, there's no air to produce lift or drag. Gravity is the main force, which has to be dealt with in space, and thrust is the force that allows a spacecraft to get into space and maneuver. A spacecraft in orbit is within the range of Earth's gravity, which holds it in orbit. Without gravity, spacecraft will fly off in a straight path. As the spacecraft orbits, it is falling, though it never reaches the ground. An object that falls through a vacuum is subjected to only one external force, which is the gravitational force, expressed as the weight of the object. An orbiting spacecraft travels so fast that the curve of its path matches the curve of the Earth, so the distance between the spacecraft and the Earth stays constant. Example of free fall is fall of an object on the moon where there is no air resistance. And another example is the fall of an object in space where there is no effect of gravity. Weightlessness is the complete or near complete absence of the sensation of weight. It is experienced while in free fall, in which the effect of gravity is cancelled by the inertia, that is the centrifugal force resulting from orbital flight. The term zero gravity is often used to describe such a condition. In space, astronauts are subjected to the effects of weightlessness. Weight is a measurement of the force on an object at rest in a relatively strong gravitational field, such as on the surface of the Earth. The weight sensations originate from contact with supporting floors, seats, beds. Weightlessness is also termed zero G. It occurs in the absence of any contact forces upon objects, including the human body. Experiments have been conducted to determine the influence of gravity and the effect of its absence in physical, chemical, and metallurgical processes. The mixing of alloys and chemical reagents without the stratification that occurs on Earth, the mixing of gases and metals to produce full metals of unusual properties, and the formation of large paved crystals are examples of the possibilities of zero gravity technology. Free fall versus weightlessness. Free fall is the situation of having zero weight of a body with certain mass and acquired when a body is in free fall or there is no gravity. Weightlessness, on the other hand, is the state in which the body experiences that the body is not being attracted by any force. In free fall, an object is falling under the influence of gravity without being prevented from falling, which implies that it is free to fall. Weightlessness is effectively net zero weight. It occurs in orbit where the gravitational force is cancelled by a centrifugal force and therefore zero net weight. Weightlessness happens because of zero gravity or free fall, and weightlessness will be experienced when in a state of free fall. These pictures show astronauts with floating food during the shuttle mission. The other picture shows Stephen Hawking in weightlessness. And the third picture shows astronauts in the International Space Station holding the first Space Olympics. Orbital decay. Orbital decay is a gradual decrease of the distance between two orbiting bodies at their closest approach, that is the periapsis, over many orbital periods. Examples of orbiting bodies are a planet and its satellite, a star and any object orbiting it, and components of any binary system. This picture shows artist's impression of a black hole accretion disk. The supermassive black holes are all that remain of galaxies once all protons decay. Effects of orbital decay: orbit termination, burning, explosion, and incineration of smaller objects. If left unchecked, the decay eventually results in termination of the orbit when the smaller objects strike the surface of the primary. For objects where the primary has an atmosphere, the smaller object burns, explodes, or otherwise breaks up in the larger object's atmosphere. For objects where the primary is a star, ends with incineration by the star's radiation. For example, comets. This picture shows Skylab Space Station Orbital Workshop in Earth orbit. Uncontrolled orbital decay brought down the Skylab Space Station. Causes of orbital decay are atmospheric drag, tidal effects, light and thermal radiation, gravitational radiation, and electromagnetic drag. Orbits decay due to transfer of energy from the orbital motion And for bodies in low Earth orbit, the most significant effect is atmospheric drag. This picture shows Mir space station with a Progress cargo ship attached on the left, a Soyuz manned spacecraft attached on the right. Relatively controlled orbital decay was used to deorbit the Mir space station. Atmospheric drag at orbital altitude is caused by frequent collisions of gas molecules with the satellite. It is the major cause of orbital decay for satellites in low Earth orbit, and it results in the reduction in the altitude of the satellite's orbit. For the case of Earth, atmospheric drag resulting in satellite reentry can be described by the following sequence: lower altitude, denser atmosphere, increased drag, increased heat, and usually burns on reentry. This picture shows Space Shuttle Discovery and its crew member heading towards low Earth orbit where atmospheric drag exerts a significant effect. Due to atmospheric drag, the lowest altitude above the Earth at which an object in a circular orbit can complete at least one full revolution without propulsion is approximately 150 kilometers, that is 93 miles, while the lowest perigee of an elliptical revolution is approximately 90 kilometers, that is 56 miles. This picture shows International Space Station in low Earth orbit, where atmospheric drag exerts a significant effect. Atmospheric drag exerts a significant effect at the altitude of space stations, space shuttles, and other manned Earth orbit spacecraft, and satellites with relatively high low Earth orbits, such as the Hubble Space Telescope. Space stations typically require a regular altitude boost in order to counteract orbital decay. Uncontrolled orbital decay brought down the Skylab space station, and relatively controlled orbital decay was used to deorbit the Mir space station. This picture shows satellites in low Earth orbit, where atmospheric drag exerts a significant effect. Tidal effects. Tidal acceleration is an effect of the tidal forces between an orbiting natural satellite, for example the Moon, and the primary planet that it orbits, for example the Earth. The tidal acceleration causes a gradual recession of a satellite in a prograde orbit away from the primary and the corresponding slowdown of the primary's rotation. This picture shows Mars moon Phobos undergoing tidal orbital decay. An orbit can decay by negative tidal acceleration when the orbiting body is large enough to raise a significant tidal bulge on the body it is orbiting, and is either in a retrograde orbit or is below the synchronous orbit. This saps momentum from the orbiting body and transfers it to the primary's rotation, lowering the orbit's altitude. Examples of satellites undergoing tidal orbit decay are Mars moon Phobos, Neptune's moon Triton, and the extrasolar planet. This picture shows Neptune's moon Triton undergoing tidal orbital decay. Light and thermal radiation is another effect of orbital decay. The light and thermal radiation emitted by the Sun is substantially more powerful than what we experience on Earth. That is because the Earth's atmosphere either absorbs or dissipates the light. Small objects in the solar system experience an orbital decay due to the forces applied by asymmetric radiation. This picture shows the total solar eclipse, the Moon, which turns off the ionosphere source of extreme ultraviolet radiation. Radiation is one of the biggest concerns for satellites since there is no atmosphere to protect their delicate internal electronics from radiation damage when they are orbiting the Earth or traveling through space. A metaplating of gold, silver, or even copper helps to protect these internal electronics by reflecting ultraviolet and infrared radiation. This picture shows heat transfer from the Sun to the Earth. Another effect of orbital decay is the gravitational radiation also causes orbital decay. Gravitational radiation is another mechanism of orbital decay It is negligible for orbits of planets and planetary satellites when considering their orbital motion on timescales of centuries, decades, and less, but is noticeable for systems of compact objects, as seen in observations of neutrons that orbit. All orbiting bodies radiate gravitational energy. Hence, no orbit is infinitely stable. This picture shows a massive object generating a gravitational field by warping the geometry of the surrounding spacetime. Satellites using an electrodynamic tether moving through the Earth's magnetic field creates drag force that could eventually deorbit the satellite. Electrodynamic tethers are long conducting wires, such as one deployed from a tether satellite, which can operate on electromagnetic principles as generators. By converting their kinetic energy to electrical energy, or as motors, converting electric energy to kinetic energy. This picture shows tethered satellite system deployment. For more information, contact Astronautics for Exploit. You've been watching and listening to Orbital Spaceflight. Thank you.